Okay. So in that case, systems with 2 or more masses. Okay. Suppose that we have a system like M2 X2 K1 M1 X1 and also F. Okay. In the 2 system, we have a solution for this system because we have 2 states in here, X1 and X2, 2 deflection, because we have 2 masses. Okay. So first of all, in order to solve this equation, draw firstly the free body diagram. Like if X1 is taken in here, X1, so we need to put to what? To M1. Okay? And so we have the F. If we pull this M1 to the downside, and so K1 resist, right? And so we need to put the K1 times X1 minus X2, because it firstly it reacts, it runs. Okay? And so if this is the case, X1 M1 X1 dot dot, and then we know that the delta F must be equals to what? The M1 X1 dot dot. Okay? See? And then we can write that the M1 times X1 dot dot must be equals to the what? The direction of X1 is downside, right? F is downside, and so this is the positive or negative. Yes, but the K1 negative. K1 X1 minus X2, right? See? Okay? Okay. And so in second place, we draw the free body diagram for X2, and so M2 X2 M2 X2 dot dot, and so if we pull X2, K1 resist or pull? Huh? Pulls? No, pull. K1 resist or not? If we going to X2, K1 resist or not in here? Huh? Resist because the K1 must be taken in here. K1 X2 minus X1. And also if we pull the X2, K2 resist or not? Resist. And so this is always the upside. Okay? And so K2 times X2 minus 0. Okay? Okay? So we can write the delta F M2 X2 dot dot, right? See? And so we can write it M2 dot X2 dot dot must be equals to the what? X2 downside. This is upside, right? Up direction. And so this must be equals to what? The minus K1 X2 minus X1. And this is also upside, up direction. minus k2 x2 times 0. Okay? This is how we can handle equations based on these properties. Okay? See? We can write it just like this one. And so we can obtain the whole equation of motion based on these informations. We need to drive or draw the free body diagram. After that, we apply the what force, and we draw the whole the forces with the direction, and just see that applying the Newton's law. This is so simple. Do you understand that? Okay. So in the third place, we need to talk about the energy methods. The spring is directly related to potential energy. So Fx, these are the spring factor, right? No, Kx, and the x must be given in here, 0 to x. And so the potential energy of this term, 1 divided by 2 times k times x square. Okay? But this is the translational, right? For the rotational form, m dt d theta, 0 to theta value. And so also, just like the previous example, k torsional times theta times d theta, it's identical, and so this can be written as the kt times theta square. This is the rotational. Okay? This is so simple. And so conservation of the energy gives us T plus V is equals to T0 plus V0, which is constant, because in the conservation of energy we preserve all the time to what? To energy. And so this is the dynamics, this is the kinetic dynamic, this is the potential dynamic, but always we have the initial conditions, initial energy in the systems. Okay? And always we have these two forms in here. And after that, we can write easily just like this one. The kinetic energy is given by, with the what? 1 divided by 2 m x dot square plus 1 divided by 2 times k x square is equals to 1 divided by 2 m x 0 square, but dot, and plus 1 divided by 2 k x 0 square. This is the initial condition, this is our dynamics. Okay? This is so simple. And after that, we can write that m divided by 2 x dot square minus x 0 dot square plus k divided by 2 times x square minus x 0 square, and always is equals to what? To 0. Okay? This is our form. And after that, we know that we can conclude that this is equals to the 0. But just remember that delta t, the change in the kinetic energy, plus delta v must be equals to the what? Is equals to the 0. Our main conclusion is that. Because if we have the energy at the initial conditions, and then we will have to the what? The dynamics from this energy. We dictate it by using these terms. Okay? Okay? So, how we can understand that? We can write the 431 obtaining equation of motion based on this information. Motion. You can see that the example can be built with what K and M if we have this value, the L is equals to what? The free length, and also we have a deflection rate in here, sigma st, just like in the previous example. Because if you put this one and gravity pulls to the what? The downside, this M, right? And so we have solved this equation in here, in the R examples, and so the solution can be given by, in these terms, solution, and so V is equals to Vs plus Vg, or equals to what? 1 divided by 2 K times, and so if we had the deflection, we can write the X, but also sigma st must be given in here, right? Right? Because we have this deflection from the gravity. And so also we have the mg x value is in here. Because this form to what coming from the mg is equals to the what? The force. And also this is the energy, right? Force times x equals to the what? Newton times meter, which means that this is the energy. So we can write this equation just like this one, 1 divided by k x square plus k sigma st x plus 1 divided by 2 k sigma st square minus mg x, right? That's it, right? And so this yields us to what? To this form. V is equals to kx square and 1 divided by 2 sigma sts square. Why? Just look at these terms. Is this equals or not? Just remember the inclined mass example. If we have the any mg gravity force in here, and so if you let the object at the what? Free, and so this what is going to downside, but at some points this is equals to the what? At the some points, right? We have, for example, in this case, sigma st is equal to this point, right? And so this mgx must be equal to this one, because this is the initial condition, okay? Okay, so if this is the potential, and also we have the kinetic. What is the kinetic, Yağmur? Yes, mx dot square, right? Okay, so just remember the previous session about what energy forms, and so the total energy is given by to what? T plus V is equals to 1 divided by mx dot square plus 1 divided by 2 k x square plus 1 divided by k sigma st square, okay? And so if this is the energy, and so in order to obtain the dynamic of this, and so we can write the d dt in the energy methods. T plus V is equals to the what? X dot x dot plus k x x dot, and the last term is equals to the what? If we take the time derivative of this terms, last term is equals to Hacer, is equals to, this is equals to, if we take the derivative with respect to the time, and so yes, 0 is equals to the 0. And so just see that the R equation is that x dot dot plus kx times x dot is equals to the 0. Okay, so x dot cannot be equals to the what, the 0, and then we will have to what, the m x dot dot plus kx must be equals to the 0. It is our equation of motion. Okay, see, you understand that? Huh? Any question? Emre? Tamam. O zaman, okay. Then we will continue with the damping elements. First of all, suppose that we have hydraulic pneumatic cylinder. Like to what? This one. We have a cylinder in here, and also we have some points in here, just like this one. And after that, we take a fill points, the gaps around this one. And so, if we push the what, the deflect the what, the x to the downside or the down direction, and so the fluid is rapidly transferred to the another section. Okay, this is how we can utilize this form. Okay, so these small holes generates some other what effect on this system, just like this one. This is the F and this is the X dot. Okay, if we pull or move this piston slowly, and then it's easily going to down, right? Everything is okay with that, and it's easily taking or pulling the water up down, up direction, right? And so, but if I increase my hand velocity, and so this resists. Why? Yes, but still we should transfer this fluid to another place. Under the velocity values or the x dot values, this creates the force, which we call it the damping. Okay? Okay. And so this creates this kind of force values, just like this one. 0.2, 0.4, 0.8, and so 300, 200, and this is the compression, this is the rebound. Okay, so if we are fast, action happens. If we are not fast, action not happen. Okay? Yes, like seat belt. Okay? So, for example, we have just like this one, M, F, and this is the what, the friction. Okay, if we are going to what, to M is moving with the what, the small velocity, and so we don't have the what, any force in here, we can draw it. But if we increase this force, and so this friction is highly affected or effective, because the heat is generated because we lost this energy. And so if we have the loss energy, we have always a damper coefficients in here, just like this one. And so we can say that this graph gives us to what? To this one, F proportional with the what? With the V value. Okay? And so the dynamics is related with what? The C coefficients in here, just like this one, the damping ratio. So in order to understand these examples, we need to continue with the 4.4.5 as the modeling mass spring damper system. Okay, so suppose that we have this kind of feature, the K and the C, and in the free body diagrams, or this is the free body diagram, but in the real life this looks like this one. Real life, we may have the spring factor in here, but we have the ground, but we have the friction force mu coefficients in here, and also we can pull this one, and so this friction returns to the force velocity relationship in here. This is a loss energy in the real life, right? We can move my hand, for example, just like this one, and so this resists because we have a friction, and so the heat is generated in here. And so how can we model this problem? Just remember the free body diagram. M, and so the F is given in here, and also the X is defined in this direction. And so if we pull the M at the right direction, and so what is the force value or the direction of the K in here? It resists or support? Resist. And so K X minus 0, because this is a fixed point, right? And so what is the C? It resists or supports? Resist. And so the C X dot 0, because this is a fixed point, right? Okay. And so the R equation can be built with what? The delta F M X dot dot. And so how we can write this equation? M X dot dot. And so just help me in here. Write the equation. Huh? Who is talking? Huh. F. Yes. Yes. And so this is the R general formula for the what? The C X dot plus K X is equals to the F, right? Okay. See? This is coming from this is a derivation of the mass spring damper system is coming from this one. Okay. So in order to understand more deeply this system utilization, we can draw another examples in here, just like this one. For example, we can define the K2 in here with the mass M and F. I'm sorry, draw it. M, F, and also we can draw, no, this is the C, and we have a point, and we have the K1. We have serial C and K1 values in here. How we can model it? This is a complex case, right? The solution can be given by the what? First of all, we need to write the what? The free body diagram, right? First of all, we have a point, and so we have a damper and K1, right? And so we need to write this is the X and this is the Y. You just put it, okay? If you have any deformations in here, C, K1, K2, and X, and so just see that M should be equalized or represented by the X, and so this point should be equalized with the Y, okay? We can do it. This is the first step. In the second step, how we can model this Y value for Y. And so we have a point in here, just see Y. And so if we pull Y to the right direction, and so K1 resist or support? He? Support mu? Resist. Allah kahretmesin sizi gerçekten ya. Ya yay nasıl gerçekten yani hani support edebilirsin? Okay. K1, and so just help me. What is the equation? K1 times Y minus X. And so if you pull this point to the right, and so C, resist or support? Oh, thank you. Okay, and so just help me. C times yes, Y dot. Okay, minus 0. Minus 0, because we have a fixed point between the C, okay? And so how we can write to what? Delta F. If we have a mass in here or not? Mass or not? No. And so this must be equal to 0. See? This is so simple. And so delta F must be written as to what? Y at the right direction, and so this is equals to the what? This one. And so this is also equals to the this one, right? Right? Huh? Okay. See, first of all, Y is going to the what? The right direction. And so K1 resist. And so the direction of K1 must be equals to the what? The left, right? And so if we pull the Y to the right, and so C times Y dot must be at the left, right? Because it resists. Okay? No, because the Y is moving. Yes, so we model it just like this one. If we pull, assuming we pull the Y, and so this kind of reaction force in here. This is the basic notation to drive this equation in here. So minus C Y dot minus K1 Y X must be equals to the 0. These are the first equation. Huh? Because we don't have any K2 connection in here. We don't have any connection to K2. Right? Okay. And so write the free body diagram for X. We draw M, and also we put the X, and so the F is in this direction. And so what about the K1? K1 resist or support? Okay, and in this case it's in the reverse direction. And so K1 and times, what should I write here? Yes, X minus Y. And so also we have K2, right? And so K2 resist or support? Resist. And so the K2 times X minus Y. Okay? And so if we have the mass value in here, and delta F is equals to M X dot dot. right? And so m x dot dot. X is in the what? In the direction of the what? Right. And so f, right direction. F k1 times x minus y is in the left direction. And so minus k1 x minus y. And also k2 times x minus 1, k2 times x minus 1. Because its direction is in the reverse order to the another one. Okay? So our dynamics can be modeled by using these terms. Okay? These are the equation of motion. Okay, guys? 1 minute. I'm sorry. Lan gözüm yaşaracak şu an gerçekten. Harbiden anlamışsınız. You are true about this. X0. K2, X0. Because we have a fixed point in here. So can we take the Laplace transform of these equations? First of all, we need to write the equation in S domain. Can be write in here. We have two equations. C dot y dot is equals to what? K1 x minus y, and also x dot dot plus K1 x minus y plus K2 x is equals to the f. Okay? We have two equations. And so, can we write the S domain properties in here? Can we convert the S domain to this equation? For example, if we have this time, and so if we take the Laplace transform of this term, c times ys times s coming from the what? Derivative operator, is equals to what? The k1 xs minus ys, right? And so if we collect the whole the terms, ys times cs plus k1 is equals to the k1 xs, right? And so if we have this equation, and then we can write to the what? Ys is equals to the what? K1 xs divided by c times s plus k1. See? If we have the xs, and so we can derive the ys here, right? Right? Emre? Okay. And so if we have the ys value, and so we can put to the another equation. This is the equation 1, this is the equation 2, okay? And so solve the equation 2 based on this information, this property, okay? And so write the xs divided by fs. This is your homework. Okay? This could be, this will be maybe seen on your midterm exam. Okay? Any question? Any question? I will share these notes. Okay? So, at this time, we will continue with the with another example. In the more complex case, 2 mass spring damper system. Okay, so if we have K1 C1 M1 X1 K2 C2 and M2 and F, okay, X2. How we can drive the equation of motion? Hajar. Yes, could you help me? First of all, draw free body diagram, right? First of all, as always, we must continue or follow this procedure. You must draw free body diagram for to what? X1, for example. Okay? And so we draw M1. Okay? And so M1 is pulling down, right? X1. And also M1 X1 dot dot, which is given in here from the Newton's law. And so what about the force? So if we pull this M1 to the down direction, and so K1 resist or supports. Okay, K1 times what? Huh? Yes, x1 minus 0. And what about the Hajar? C1. C1 supports or the resist? Resist. And so, what about the equation? Yes. Yes. Why 0? Yes, this is the fixed point. See? Okay. And so, what about the K2? K2 resist or supports? Resist. And so, the direction must be given by this one. C2. Okay. The direction in the reverse. See? And so, this is the K2. And so, what about the K2? X1 minus X2. What about the C2? Yes. In the first place, if I pull this equation and so the X1 is moving first. And so the first term must be equal to what? X1. Okay? After that, that's simple. Delta F is equal to what? M1 X1 dot dot. Okay? And so M1 X1 dot dot is equal to what? If is there any F in here? Yes, we don't have. And so just write X1 is going to the what? To down. And so K1 X1, right? This is true? Huh? Yes, minus. And so plus C1 X1 dot, right? Oops, thank you. This is minus. And so plus K2 X1 X2 because it's the downside, right? Thank you. This is also minus. And so minus C2 X1 dot X2 dot. So the R equation of motion is equal to the what? For the M1? This. Okay. In the second place, we have Q. Draw free body diagram for X2, right? And so, firstly, Emre, what do we need to do? Okay, M2 and X2. And so we have M2, X2 dot dot, right? And so we need to define the forces. We have K2, C2, F. F is going to the what? To down. This is given. But K2 is resist or not in here? Okay. C2? Okay. This is the reverse direction. And so, what is the K2 times? Why? Because X2 is moving first. X2 minus X1. What about the C2? Yes, thank you for everyone to contribute to these formulations. And so, in this case, delta F M2 X2 dot dot, and so M2 X2 dot dot is equals to the what? F minus K2 times X1 and C2 X2 dot X1 dot, right? So this is the R second equation of motion. And so we can easily drive the equation of motion based on these techniques, right? And so I need you to, this is the example or the homework for you, x1s fs and x2s fs must be written from this page. Okay, you can drive it easily right now, right? See?